Welcome. In this course, we're going to learn about machine learning. But first, let's answer the question, what is machine learning? But I think before we can ask, what is machine learning? I think we need to ask, what is learning? Think about the word experience. Learning is really based on a sum total of experience. And really, why do we learn? And I think ultimately the answer has to be to improve our experiences in life. And our experiences help us predict our future. They help us enhance our lives through future prediction of possible outcomes. Our experiences help us to predict the future. But why would we want to actually predict the future? Why do we want to predict? And I think ultimately the answer comes down to improve our chances of a positive outcome, to have a much more rich and fulfilling outcome in the overall experiences of our lives. When we make predictions, we actually also use it to make decisions. And a lot of our decisions are really and truly based on our experiences, and they are based on our prediction of that positive outcome. And of course, not all predictions can come true. Not all predictions are within our grasp. For example, we can't consistently predict the winning numbers in the lottery. But when we make predictions about things like touching a hot stove, based on our experiences, we know what that outcome is going to be with absolute certainty. So when we look at the idea of experience in learning and predictions, we introduce our ability to make the best possible decisions that we can. And that's really one of the driving motivators for machine learning. And as humans, we make decisions thousands of times a day. And it is usually based on something likely to be true or likely to be false. And so as human beings, we don't really have a set of programmed instructions in our head. We just somehow intuit based off all of our experiences. But when we compare that to computers, to software, they are following very specific sets of instructions. And we program a computer to do things based on all those conditions. And so when we try to program all of these very specific outcomes into a computer, our code can become absolutely enormous. And when you look at this, imagine trying to use old-fashioned programming to have robots drive a car for us. Imagine all the scenarios that they could come up with that they would have to be able to account for. Imagine the life of the programmer trying to get a robot to behave like a human based on all of these sets of possible combinations of inputs and outputs. It would be extremely difficult. But when we look at children, when we look at, starting off, children are very indoctrinated at a very early age to driving vehicles. They have go-karts, they're passengers in people's cars. And over decades, they gain experience in driving. And they're not following sets of algorithms consciously inside their head that says when to turn, when not to turn. They're just intuiting the behavior of the vehicle and the rules of the road, and they're becoming successful. But organically or inorganically, in the background, we are following algorithms. And really, when we look at an algorithm, we oftentimes refer to it as a mathematical or a computer science algorithm. Okay, and what this definition from Wikipedia says is that's a finite sequence of well-defined computer implementable instructions, and that we typically solve a problem to perform a computation. And so we use algorithms as human beings. We just may not be aware of it. But computers constantly use algorithms. And if you're wondering, sometimes we are aware of it. When we follow a recipe To bake a cake, for example, that is an algorithm. Your recipe is an algorithm. But ultimately, the goal in machine learning is to treat it like a very young driver and give it thousands of hours of driving experience until you can have 30 to 40 years of driving experience, where we don't have to program every possible outcome, every contingency. What we do is we allow the computer to gain its own experience. Machine learning really does break down into two major categories. There is prediction and clustering. And the majority of what I want to talk about now is actually prediction. And prediction really encompasses something called supervised learning, whereas clustering is more in the realm of what we refer to as unsupervised learning. Prediction can now break down into two very distinct categories as well. So there's regression. And as an example of regression, we look at this sort of model here of house sizes versus their price. And we can make the prediction off of this regression. And then with classification, with this particular example, we look at getting email. And the classifications really become, does it go to inbox or does it go to my spam folder? And so we have these two sort of domains within prediction. And these domains will actually break down into further subsets. Before I talk about that, you can see the reference down to the bottom of the screen. There's a wonderful blog about key concepts in data science. And I want to use that to look at some of the very common terms that we're going to use. And the first one is a model. And a model is a mathematical representation of a real world process. A predictive model forecasts a future outcome based on past behavior. Now, training. What is training? And training is a verb. It is the process of creating a model from the training data. The data is fed into a training algorithm, which we briefly spoke about, which learns a representation for the problem and produces a model. This is also called learning. And we've got classification. So classification is a noun, a prediction method that assigns each data point to a predefined category. We have a training set, which is a noun, a data set used to find potentially predictive relationships that will be used to create a model. What's a feature? And a feature is also known as an independent variable or a predictor variable. A feature is an observable quantity recorded and used by a prediction model. You can also engineer features by combining them or adding new information to them. An algorithm, and we spoke about the algorithm already, a set of rules used to make a calculation or solve a problem. What's regression? It's a prediction method whose output is a real number. That is, a value that represents a quantity along a line. Example, predicting the temperature of an engine or the revenue of the company. And we talked about predicting house prices already. What's a target? In statistics, it is called the independent variable. It is the output of the model or the variable you wish to predict. Very important. Overfitting. A situation in which a model that is too complex for the data has been trained to predict the target. Now pay attention here because it's important. This leads to an overly specialized model, which makes predictions that do not reflect the reality of the underlying relationship between the features and the target. And lastly, what is our test set? Our test set is a data set separate from the training set, but with the same exact structure. And we use it to measure and benchmark the performance of various models. Now, throughout all of these definitions, you kept seeing the term model come up. And it's because your model is so important in everything that you do at the very beginning in order to get the desired output that you're looking for. So the model is extremely important in machine learning algorithms. In machine learning, we have algorithms and models that we've talked about. And really, this can be broken down into three distinct groups. And the first one we have is linear models. We have tree-based models. And what's more and more popular every day is neural networks. And when we look at what a linear model is, it simply uses a formula to find the best fit through a set of data points. And this actual method goes back a couple of hundred years. And it's been widely used in statistics and now in machine learning. And what makes it really good is its simplicity. The variable you want to predict is represented by an equation of variables you know. And so prediction is just a matter of inputting the independent variables and having the equation spit out the answer. This also breaks down into a couple of subsets: linear regression and logistic regression. And the next thing that we have is our tree-based models. When you think about this, think about a decision tree, a sequence of branches. Okay, and this again breaks down into further methodologies or techniques of tree-based models. And we've got random forest and gradient boosting. Finally, we get to neural networks. And neural networks have become probably one of the fastest growing or most popular forms of machine learning algorithms. And these break down into something called deep learning. And this is an example of a multi-layered neural network, which is, again, sometimes referred to as deep learning. And one thing that has really and truly captured the imagination of the general public with regards to artificial intelligence is this idea that scientists are creating a human brain or a model of a neural network which is modeled after the human brain itself. And for non-artificial intelligence scientists or practitioners, we know that there are many different techniques that we can use to employ machine learning. But this one is really the one that captures everybody's imagination more than any other. After all, maybe it's just a sense of flattery that we are trying to create a new form of intelligence modeled after our own actual being. And so when we're looking at our models, and we know that we have to break our data up into two sets, for example, our training set and our test set, how do we know if we've actually made a really good model? And ultimately, the answer to that is it depends whether you're doing regression or classification. We're going to use these two metrics to evaluate our models. And the first one is regression. And we use these different things called mean square error or R squared. And in the case of classification, we look at accuracy or something called the AUC or area under the curve or logistical loss. Okay, so these are the two ways that we can go in and do evaluation on our actual models. Okay, and we have this concept of overfitting. It can be one of the biggest challenges to building predictive models. And to account for our overfitting, we do this technique called regularization. And so we have tools to overcome the challenges of evaluating the models. And we're going to explore those in the future. And in the past, what we've done is kind of outlined in general terms what really machine learning is all about. What are the steps? And we want to import our data set. And the next thing is we've got to clean the data or reorganize the data into something that's very useful to us. And once we've done that, we want to split that data up into two groups, which is usually our training set and our testing set. Then once we've established that, then we want to create this model of it. And once we've got the model that we're happy with, for the most part, we want to start to train that model. And we're going to use two variations of the model. We've got the training set and we'd have the test set. And once we have all of that established, then we can go in and now make our actual prediction for the first time. But what about evaluating this or improving it? And really, that's the next thing that we want to do. This really becomes our opportunity to ask the question, how good is our machine actually learning? And so we have these two strategies that we want to look at to do this. We can train it with some validation and this test. And we refer to this as our holdout strategy. And another method that we can possibly use is something called our K-fold strategy, where we take the entire training set and instead of doing the minor validation, we go straight to testing. And keep in mind that these are cycles. Okay, it's a constant cycle of training and testing and training and testing. And of course, I want to just point out something that in the early stage of this, we may not have actually picked out the right model. We may be using linear or tree or other. We will go through this and then reevaluate whether or not we think that the model we chose was the appropriate one. And then finally, after that, we can then go ahead and make a final decision based on some of the evaluation that we've done. And we can select the best final model. So for example, maybe a decision tree does turn out to be the best model for what we want to achieve. And we've talked a lot about prediction so far. And the majority of what we've been discussing has been prediction. But what about clustering? We mentioned it, but what about clustering? And clustering really belongs to something called unsupervised learning. And the aim of unsupervised learning, it's not predicting, we're searching for a hidden pattern. Okay, and that is a huge distinction between supervised and unsupervised. In supervised, we know what the data is, and we have a reasonable expectation of testing it out because we have a sample size that allows us to break it up into these two parts that we talked about, the testing and the training. Okay, but in unsupervised learning, we don't have those data sets in that sort of a manner. And so our goal with unsupervised learning is to search for the hidden pattern within our entire data set. And you can see here, we've got these two clusters, and we're looking for those patterns within these clusters. And there's something else called a k-mean that uses clustering. Once we discover or uncover what the pattern is, then we can take that pattern and then begin to convert that into something that we can predict. So we've talked about supervised learning, we've talked about unsupervised learning and all the different models and algorithms, but where does this all fit into artificial intelligence? Because artificial intelligence really is a family of many different techniques, many different forms of science and disciplines. And one of them is something called computer vision. We have other examples where we're doing biometrics and we're doing robotics. All of those may or may not rely on this idea of machine learning. And again, within machine learning, we talk about linear, we talk about trees, and we're talking about neural networks. But as an entire family of artificial intelligence, all of these have varying combinations of one another. To say that machine learning and AI are the same thing would be, in fact, incorrect. And oftentimes they are used interchangeably. Consider AI really is the all-encompassing circle on this Venn diagram. And all of these different techniques fall within the realm of artificial intelligence. And so what we really want to do now is just focus on the realm of machine learning and all of its different algorithms and models and techniques. And we're predominantly going to spend all our time in supervised learning, but we will touch on this idea of unsupervised learning. So ultimately, our goal is just to focus on this one ever critical piece of artificial intelligence. So I hope that gave you an overall macro view of really artificial intelligence and also how machine learning ties into it. So thank you for watching, and I'll see you in the next video.